Hello guys, welcome to the machine design world. This is Keval Patil and today we are going to see case 2 and case 3 of bolted joint which are eccentrically loaded. We already covered introduction and case 1 in last two videos. Just find the link of those videos in description. So let's start with case 2, eccentric load perpendicular to the axis of bolt. That is nothing but shear and tension. Actually, what does it mean? Perpendicular to the axis of bolt. Okay, now see here, this is the frame. Okay, this is the frame. Load is acting over here, and bolts are here and here. Okay, so there are three bolts: first bolt, second bolt, three bolts, and their axis is, this is the axis of the bolt. Okay, so they are having like this structure. They are having like this structure. Okay, so like this or like this. Okay, so now this is the axis and this load is perpendicular to the axis. So eccentric load perpendicular to the axis of bolt. Okay, so this axis is perpendicular to the load. Okay, now which stresses this load is causing in the bolt? Okay, now see, this first thing is just remove this load and put on the eccentricity. So this whole frame going down like this. Okay, this whole frame will go down like this. Let's see, this is the bolt. Okay, and this is a load. Now this is fixed, it is wall, just consider it is wall. What will happen with this load? This whole body will come down. Okay, it will be causing failure of bolt over this section. Okay, so bolt will fail like this. It will be in two parts. It will fail into two parts. Okay, like this. First part will be like this and second part will be like this. So this is the failure. This is the axis of the bolt. Okay, this is the failure. See the line of action of load. This is the line of action of load and this is the line of action of cross section area, failure area. So both are the parallel, then it is the shear load. So first one is direct shear. Now this load is causing bending like this. So this bolt, these bolts going to bend. They're going to bend like this. Okay, so they're going to bend like this. So if bending is like this, then this will be tension and this will be compression. So second load is, we consider tension. We don't consider compression as a design criteria, as it tends to close the gap. If you having this structure and there is some crack, then what will the compression load do? It will try to close the gap, whereas tension it will try to open the gap. That's why we consider tension as a failure criteria. So in this case, first is direct shear stress is acting and then second is tension, or you can say bending. Bending is nothing but we consider as tension. So that's why shear and tension. Okay, so what is a given? So first now we will see the problem. A cast iron bracket is fixed to the steel structure. This is steel structure, this is cast iron bracket. Support a load of 7.5 kilonewton. So load is given as 7.5 kilonewton. There are three bolts as shown in the figure. 3 bolt, bolt 1, bolt 2, 3. So there are 3 bolts. The bolted will be like this: first bolt, second bolt, and third bolt. Okay, and this bracket will be like this. Okay, it will be like this. If you have the side view, it will look like this. Side view will look like this. Okay, so 2 bolts over here, 1 bolt is here. If bolts are made up of 45 C8, that is material of bolt, plain carbon steel 45 C8, and yield stress of 380 Newton per mm square, factor of safety 2.5. Specify the bolt size. So force is given 7.5 10⁻³ Newton, yield stress is given 380 Newton per mm square, factor of safety 2.5, and eccentricity 250 mm. So eccentricity 250 mm. Now this distance is given 25 mm, this is 175 mm, and this is 25 mm. So this distance is called as L1. Okay, and from this, okay, and the bolt distance is is L2. What is this? This edge is known as tilting edge. What is tilting edge? When you applying this load, this whole structure going to rotate like this, and it will rotate about this tilting edge. This edge will come out, edge will come out, but this edge will stay at its point at this position, and this whole body will rotate about this edge. So this edge is known as tilting edge, and distance from this tilting edge to the bolt is called as L. Okay, so L1 is distance of bolt 1 from tilting edge, L2 is distance of bolt 2 from tilting edge. Similarly, L3 is distance of bolt 3 from tilting edge. Now, why this L1, L2, L3 is required? So if you remember the secondary shear stress formula, there we were taking R1, R2, R3. We are going to use the same formula, but there we will take L1, L2, L3. We'll see the problem, you will come to know. Okay, so we'll start with permissible shear stress. So first we will find permissible or maximum shear stress. Okay, permissible shear stress. So permissible shear stress will be tau max is equal to 0.5 into sigma t is equal to 0.5 into sigma t is nothing but sigma yield 380 divided by factor of safety. Okay, so it is nothing but 0.5 into 380 into factor of safety is 2.5, that is 76 Newton per mm square. Again I am telling, for bolt we use mild steel most of the time, mild steel as a material. Okay, now it is also having plain carbon steel as a material. So steel, we are using steel, that's why which theory is applicable? Maximum shear stress theory. For brittle material, maximum principal stress theory. Okay, for ductile material, maximum shear stress theory and one masses theory. So according to maximum shear stress theory, what is value of tau max? So tau max is equal to 0.5 sigma yield upon factor of safety. So same formula over here. So we'll get 76 Newton per mm square. So next is primary shear load or direct shear load. I'm just going to direct because we are not having two shear load. So direct shear load. So same formula from earlier sum. It is nothing but P/1 is equal to P/2 is equal to P/3 is equal to P/4 is equal to P upon number of bolt. So P is 7.5. Okay, there is no PS4, only 3 bolts upon 3, it is equal into 10 raised to 3. So 2.5 into 10 raised to 3 Newton. Alright, so we are having primary shear load as 2.5 10 raised to 3 Newton. Now with this we also have to find primary shear stress. Okay, so direct shear stress. Direct shear stress. So it will be tau is equal to primary shear load PS upon cross section area. So it will be 2.5 into 10 raised to 3 divided by AC Newton per mm square. Alright, so I think up to this much it is same what we have done in the last questions or last video. Okay, now see this direct shear load, up to this we know only this much is new part, direct shear stress. We are having two different stresses, shear stress and tensile stress. One stress we calculated. Why we calculated, that you will come to know soon. So we'll go for next step, that is tensile load. Tensile load on bolt. And 3. Why bolt 2 and 3? Okay, so what is formula? So I'm just doing F tensile 2 is equal to F tensile 3 is equal to same formula, PE upon L1 square plus L2 square plus L3 square. Now here we having instead of r1 square plus r2 square plus r3 square, we are using l1 square plus l2 square plus l3 square. Remember, there are only 3 bolts, so you have to use l1 square plus l2 square, l3 square, no l4 square. Now this into multiplication something like if 2 there then r2, if 3 there then r3, but here we are not having r2 r3, here we are having l2 and l3, so l2 and l3, so this distance. Okay, so what is this distance? So this distance is 25 plus 175. So I'm just writing L1 is equal to 25 mm and L2 is equal to 200 mm. Right? So L1 and L2 and L3 same. So we will get here L2 or L3, whatever you want you can write. So it will be like something 7.5 into 10 raised to 3. What is eccentricity? It is given as 250 into L2 200 whole divided by L1 is 50 square plus 200 square plus 200 square. Alright, so you will get something 4651.61 Newton as a load. So you know now you have a tensile load, so just find tensile stress. Tensile stress on bolt 2 and 3. So what will be the value? Sigma T is equal to this load FT2 divided by cross section area. Again same value, so you will get 4651.61 divided by section area square. Now at a time on every bolt or just heavily loaded bolt, that is 2 and 3 here, heavily loaded bolt is 2 and 3 here. Okay, bolt 1 is not carrying that much load, so bolt 2 and 3 having highest load. So at a time on bolt, direct shear stress is acting and also tensile stress is also acting, so we have to use principal theories. Okay, so which failure theory is applicable? Okay, so again bolt is having ductile material, so for ductile material I have already told we use maximum shear stress theory. So maximum shear load according to maximum shear stress theory is tau max is equal to under root tension by 2 square plus tau square. So this is formula for maximum shear load in maximum shear stress theory. Now we know tau max value we have calculated, it is 76 Newton per mm square. Okay, so 76 is equal to root, what is sigma T? 4651 point sigma by 2. Okay, and AC also there, plus what is tau value? Tau value is 2.5 into 10 raised to 3 divided by AC. Okay, just put all this term in, solve for X equation and find value of AC. So we will get AC value as 44.928 mm. Now you can go to the PSG 5.42 and there you can find what is the value of area. You have 44.928, so area, so it is 36.6. so next is 58, so it is lying between this, so consider highest value from this, so it is 58. So now it is 58, so we will select which bolt? M10 bolt is selected. M10 bolt is selected. Okay, so from PSG 5.42 selecting M10 bolt which having D is equal to 10 mm. Okay, D is equal to 10 mm. You can see over here which is having M10 bolt, so major diameter is 10 and minor diameter is 8.16 and DC is equal to 8.16 mm. Hopefully you have understood this sum. Okay, then we will move to the case 3, which is easiest one. Okay, let's start with case 3, that is eccentric roll parallel to the axis of the bolt, that is tension case. Now see, this is the bracket. Okay, this is the bracket and load acting over here. Okay, two bolts are there, 1 4 and 2 3. Okay, sometimes 2, sometimes 6 bolts are there. Okay, now there are 2 bolt, 1 4, here 2 bolt, 2 3. So 1 2 3 4 bolts are there. Now bolts are having axis like this, bolts having axis like this. Okay, so they are having axis like this. So 2 bolts here, 2 bolts here. First we will remove this load, we will keep on eccentricity or CG. We will remove the load from eccentricity and we will put on CG. Which stress is causing? This load is causing tension stress. Like if the axis is like this, and load is acting along the axis, then we will call it pull force, that is tension. So direct stress is tension over here. In last two cases that it was direct shear, but now we are having tension. So this is tension. And second is, it is bending like this, it is bending like this. So it will cause this bolt is like this. Okay, after application of load it will bend like this. So this bolt will bend like this, So here is tension, here is compression. Again we'll keep tension as a design criteria. So that's why tension. Alright, so now which is tilting edge? See, if it is moving like this, it will break from here, it will move, and this tilting edge will be there at position, all its position, and whole body will rotate along this tilting edge. So this edge will be tilting edge. This is moving, this is just keep that edge at a point and remove and move the body should move total circle at that edge. Here it won't move, here it will break and it will come out. So this one is tilting edge. Okay, now this is bolt 1, so L1, this is bolt 2, so L3. Now my question is, okay, let's move the question. Okay, L2, L1, L2, L3 value is given. Question is a cast iron bracket as shown in figure, having a steel structural support and load of 25 kilonewtons. F is 25 kilonewton. There are two bolts at A and B. This bolt 1 2 3 4 numbering is not given, only A and B is written, and they have said like there are two bolts at each A and B, means number of bolts are 4. If permissible tensile stress is 50 Newton per mm square. Now sigma T is given 50 Newton per mm square. Determine the size of bolt. What is given? L1 is given, L2 is given. My question is, what is E? What is eccentricity? So see, the eccentricity will be this distance. So this will be the CG and this will be the eccentricity E. Now how to find this eccentricity? So for that, we know this L1 distance, it is 50-50, and we know this L2 is 200. Okay, I will know this L is 400. Okay, I want this distance. So first I will try to find this distance. Okay, this distance, then L minus this distance is equal to E. Okay, so what is this L1? I want to find this one. Okay, so this is L2. Okay, and this is L1. So this distance will be L2 minus L1. So this A to B, this distance is L2 minus L1. It is nothing but 150 mm. Alright, this distance is 150 mm. Then this distance is this, just I'm mentioning it as X. So this X will be 150 by 2. So it is 75 mm. So now I know this total distance. I will just minus this distance from L. I will get eccentricity. So eccentricity will be L minus L1 minus 75. So I will get L is 400 minus L1 is 50 and this is 75. So I will get 275 mm. I will get 275 mm. So L E is equal to L minus L1 minus 75, that is 275 mm. So I just wrote down the given parameter. P given is 25 into 10 raised to 3. Number of bolts are 4. L1 50, L2 200, L4 it is L 400 mm. Sigma T is 50 and E I found out 275 mm. Now we will go to the first step. So we know two tension stress are there in the every bolt. So first is primary tension load. Okay, it is nothing but primary tension. So FT1 is equal to FT1 is equal to FT2 is equal to FT3 is equal to FT4 is equal to F upon number of bolts. So F is given as 25 into 10 raised to 3. Number of bolts are 4. So it's equal to, we'll get 6250 Newton. Right. So remaining is secondary tensile load. Now tell me which bolts are carrying high load or heavily, which bolts are heavily loaded. Okay, so now see the bolts which are having maximum distance from tilting edge will be highly loaded. Alright, so now it is 2 and 3. Okay, so L2, because we know the formula, it is nothing but, I'm just writing the formula, okay, for secondary load, that is PT2 is equal to PT3 is equal to P into E into L2 divided by L1 square plus L2 square plus L3 square plus L4 square. Okay, now we know that for PT1 and PT4, here we will have L1 and L1. This is a constant and it is the same. This value is same, only variable value is this one. So if I put 50 over here, then I will get less value. If I put L2 value, that is 200 over here, then I will get more value. That's why PT2 and PT3 are heavily loaded. Okay, now I will try to find 25 into 10 raised to 3, eccentricity is 275 into L2 is 200 divided by, now L1 and just I'm adding 200 square plus 50 square plus 200 square plus 50 square. So you will get the value as 16176.5 Newton. Okay, so we got secondary tensile load. Now we'll go for resultant tensile. Here we have used wrong notation. It should be PS2, PS3. Okay, so shear load, secondary load. This is primary load, secondary load. Okay, and this should be FP1, that is primary. Okay, so FP1, FP2, FP3, primary on one load. Okay, this is PS2, or you can say FPS. It's all right. So now resultant tensile load is resultant tensile load on bolt 2 or 3. Okay, so it is nothing but resultant bolt on 2 is equal to force primary on bolt 2 plus force secondary on bolt 2. So it is something 6250 plus 16176.5 Newton. You will get 22426.5 Newton. Then you want to find bolt size. Okay, bolt size. Okay, why we added these two? Why we added? Because both are the tensile load, both are acting on the same axis. Okay, so we added these two. They are not having any angle in between. Now bolt size will be sigma t tensile upon P2 divided by cross section area. Now we know the sigma t, it is given 50 is equal to PT we having 22426.5 divided by cross section area. So now what is a AC? AC is given as, from this you will get 448.5 0.52 Newton mm square. Okay, so now you're having areas 448.52. So go to the PSG, find the area. So it is 353, in between 353 and 561. Okay, so you will select higher value, that is 561, and the bolt is M30. Okay, so bolt is M30 from PSG 5.42, selecting M30 bolt. Now what is D? That is 30 mm. This 30 represent the outside diameter, and DC, let's check on PSG. This is M30, this is 30 is outside diameter, and this column represent minor dia, that is DC 25.706. 25.706. Okay, so this is end of the case 3. A simple problem as compared to the case 1 and case 2. Okay, hopefully you have understood the design of bolts. Okay, comment on video and let me know whether you understood or not. Thank you for watching the video.